Okay, we are moving into multivariable calculus. So multivariable calculus isn't just adding one dimension to one-dimensional calculus. It's more like one-dimensional calculus squared, because there's a lot of different ways that, a lot of different directions that it can go. Because when we say multi-dimension, we can mean that the domain is multi-dimension, but that we're going to a single other dimension, or it could mean the opposite. It could mean from one dimension to multiple dimensions, or it could be both of these together, from multi-dimensions to multi-dimensions. And each one of these has its own difficulties and sort of characteristics and things, and they're all related. So in this video, we're going to talk about curves. And curves are this one, which is one dimension into multiple dimensions. Then the next video, we're going to look at real valued functions, which have a multidimensional domain, but the values of the function are real valued. And then finally, we'll look at vector fields, which are basically these, which are basically from multidimensions to multidimensions. So curves actually fit, in a way, they're actually vector fields, because they're not a field though, but they're vector valued functions, because they go from one variable to multivariables. So what a curve is, if you just think of a curve that you might draw on a piece of paper, the way to think about a curve is just imagine a particle in space that moves over time. So as time is in an interval from A to B, so as t moves along here, then the particle is going to move along here, and this would be like, f of t, or f of a, and f of b. So this could be 3 dimensions or more dimensions. Then in the next video, we're going to look at the opposite, which is when you might have it's always harder to draw these, but you have a 3-dimension, you might have a domain that's in x and y, and then some kind of a curve. So the values are in z, and each value of x, y gives you a value of z, so overall they make a surface. Okay, so this will be next video, but so here we're just going to focus on curves. So we define a curve as a function, which we call it a path. So the path is a function, ct, over time, over some interval from a to b, into Rn. And then the collection of points, the image of this function, is what we call the curve. So the function is the path, and the image is the curve. And then CA and CB, I called them F here, but CA and CB are the endpoints. And then this path, this map, is said to parameterize this curve. So furthermore, if C is a path in R3, we can write CT equals xt, yt, zt, and then we call x, y, and z the component functions of C. And then it's the same for R2 and generally in Rn. Okay, so to me, this is one of the hardest things to accept or to believe about parameterizing a curve. That if we have ct equals xt, yt, and so we have two functions, and then they make some kind of a curve here. If you don't think about it, if you just kind of accept it without thinking about it, it's like, okay, fine, that's how we'll deal with it. But to me, I'm not immediately convinced that if you have two functions, so you have like, a function f of x, or let's say x of t, and this is t, that goes like this, and then you have another one, y of t, and this is t, it goes like this, and you put these together, that it's going to make a smooth curve like this. It's kind of interesting. To me, it seems almost too convenient that you can just decompose this complicated thing into two one-dimensional functions, and that you end up with that. Or how are these two related? Because they seem independent. What if y goes the wrong way or something? And the point is that they are actually they're defining the same thing in a way, and they are in fact locked together. The two functions are not independent when we're talking about this curve. There is a curve that these two functions create. So they're dependent in the sense that both of them, for any value of t, have a particular value of x, and that doesn't change because x and y, the functions are defined. Given that, c is just another way of picturing how these two relate as you move along t. And so you can almost think of it as like a toy where you have like two sliders that go back and forth, like an Etch-a-Sketch. So you have two knobs. So as you turn the left knob, the pen goes left and right. And as you turn the right knob, the pen goes up and down. There's no way to jump. You can't remove the pen. No matter how quickly you turn it or how far you turn it, it's always going to be touching the screen. It's always going to be making a continuous line wherever you go back and forth. As t changes, it's going to change in a continuous way as well. So that means that x and y have to be smooth. So then whatever it is that they're drawing out has to be smooth as well. So the way that I think of it that I have trouble believing is that if you take a curve, you can just name the two functions, the two one-dimensional functions that will create this curve.
We'll return after these messages.
I have to interrupt myself here because as I was reading up for this video, I came across something that I think is really amazing. It turns out that's not an easy question. Every curve can be parameterized, but not in a straightforward way. And what can and can't and how they can be is actually a very interesting question. It turns out elliptic curves are actually a family of curves that cannot be parameterized in a simple way. So this topic is so interesting, I think it's worth a video on its own. So next week I'm actually going to talk about what I learned about this. Then we'll go back to surfaces and calculus after that. But if you think of it the other way, then any two functions, because they're both continuous, they're going to create a curve from one point to the other. And so I just want to look at a couple examples with a graph. Just randomly, let's try xy equals t squared cosine t and 50 sine t. You can hardly see it. Oh, look at that. Oh, that's cool. So this just makes these two functions make this graph. So if you just think to yourself, you can put any two functions, x and y, as the parameters, and it's going to create something because they're both smooth, and as one goes up and down, the other one will also be going up and down in a smooth way, and they will make a curve. Then that makes it maybe a little easier to see that they're connected. This is just another way of looking at the two functions here. Okay, there's one more thing that I want to call attention to before we move on, and that is that when we talk about an object like this, we both talk about it, sometimes we talk about it as a point in space, and sometimes we talk about it as a vector. And it doesn't really matter because the math is the same regarding both of them. But in terms of visualizing them, it makes a big difference. If we have a curve here, just to make it interesting, a spiral. So actually I can just write this down. This would be something, that would be, if it was like this, this would be xy equals t cosine t. So t cosine t, so the radius gets bigger as it goes out. If we think as t goes from A to B, we can think of it as a particle in space, as a point in space getting, moving around this spiral as time goes by. But we can also think of a point here as the vector. And you hear this all the time in multivariable calculus, that sometimes we're thinking about the point in space, sometimes we're thinking about the vector. And what I want to point out is that you can think of this function either as carving out a line, a curve in space, or completely differently, and actually as a function how the vector itself changes over time. So it's here, 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 and it's getting longer and it's rotating as time goes by. That's a completely different way of thinking about what these are. When you think of a vector as a pair of numbers like this, then the picture of a vector is from the origin out to the point. So what this is doing over time is that vector is changing. It's getting shorter and longer and rotating one way or another and back and forth and so on. But it's not at all, in that case, a curve through space. It's actually just describing the action of a vector over time. It gets shorter and longer and rotates back and forth. So I just want to keep this in mind, because there's something very different going on here than a normal, just a simple vector. If we have a simple vector, 2, 1, that would just be a line that goes out here like this, right? This is static. But this isn't static. It's actually describing changes over time, and it's changing the entire vector. If you have an equation of a line, if v is 2, 1, then if we graph that, t is all that's changing here. So if xy is, say, 3, 5, we might be up here somewhere, and then as t varies, we're adding the vector to it, and it might get longer this way, or it might go longer this way, and we're starting it from 3, 5. But the thing is, at all times, you can think of this either as a vector or as just a point in space, because a vector itself does not actually have a location in space. A vector is only a direction and a magnitude. When we say like, oh, we can start it here and go off this way, or if you add two vectors, one goes this way and one goes that way, this is a little bit misleading, because there's not really a vector that starts here and goes that way. The vector itself is just the object that has this direction and this magnitude. Here's another object that is this direction and this magnitude. And you can see them graphically. This is a way to think of what it means to add them. I'm running out of room here. A better way to do it might be to imagine you have a boat that's going forward in this direction while the wind is coming this direction. What you're actually doing, if you're wondering where is the boat going to be at time 3 or whatever, then the wind's going this way, the boat's going that way, and so if you add the two vectors together, it's going to be up here. So the boat's going to kind of go in the direction it's going and then also be pushed by the wind. So it's not really what's going on when you add two vectors. You're not really putting one at the tail of the other. That's just a way to find the total, but it's not really how you go about. It's not really what you're doing when you add two vectors. Let's try a more complicated example. So let's imagine there's a wheel of radius capital R, and there's a point somewhere on that wheel that is small r away from the center. And this wheel is rotating to the right at a rate of v. So what we want to do is we want to find the path that describes the motion of the point as the wheel rotates to the right. The first thing we'll do is we'll place the wheel along the x-axis so that the center at t equals 0 is 0, r. So it's r above 0 and it's at 0. And then the speed of the center of the wheel as time goes by is just v times t. So we'll call that capital C is just vt, r. The equation that we're looking for is lowercase c, which will be the path of the r as the wheel turns. And that will be the center plus the position of the point relative to the center of the circle. So if this is the origin, and so the wheel has rotated a little bit, particle's up here. So what we're looking for is ct, which is the position of the particle as it rotates. So we can do that by taking, here's the vector of the center of the wheel, that's ct, and then this would be the vector of the particle relative to the center, call that dt. And so to find ct, it's just the center of the wheel plus the position relative to the center is dt. So again, look at, from what we were just talking about, we're looking at these as vectors and imagining that this vector goes to the center, and then this vector is the particle relative to the center, and then you add those together and you'll get the position over time. But this is a perfect example where when you're thinking about vectors, it can be kind of confusing to think about it that way, because we're really thinking of this as a particle that's carving out some kind of a curve in space. But what we're ending up with as time moves on, at time 0, the c vector, the capital C, is straight up. And then as this rotates to the right, the c vector keeps moving over and over. Or we can look at that just as the point in space is moving further to the right. And then you add d to it, and you're going to get where the position of the particle over time. Okay, so you can see how sometimes to me it can be confusing to think of motion like this as the vector changing, when it's easier sometimes to think of just the particle moving along. But whenever the particle's moving along, you can also think of that as the vector rotating and expanding over time. Okay, so to find CT, we need the center plus the position relative to the center. So we have to figure out the position relative to the center. The radius is r. First, let's think of the rate at which it's rotating. The circumference of the circle is 2 pi r. And so it's going to move to the right 2 pi r at some time t. So if we divide the r by both sides and then we move the 1 over t over and divide by 2 pi, then angular velocity is just v over r. Radians per time is you divide that rate by 2 pi. Okay, so dt is going to equal the radius times cosine of the angular velocity. Oh, the other thing to remember though is that it's going clockwise, so we need to make it negative to make it go clockwise. So it's v over r times t. Now, it depends on where it's starting. So there's some plus some angle, which is the initial position of it, comma r times sine minus v over r t plus some angle. So in this case, it's minus pi over 2, right? Okay. So plug in that, and then dt equals, and then we're also going to use some trigonometry identities here. So here the angle is minus pi over 2. Here the angle is minus pi over 2. When you shift cosine and sine by minus pi over 2, that makes cosine into minus sine. So we have r minus sine of minus v r t, but sine, there's another identity that says that sine of minus theta equals minus sine theta. So this is a minus and this is a minus, but then we can make them both plus, comma. Sine turns to cosine, and then the other identity is that cosine of minus theta equals cosine of theta. So we can just get rid of that minus because this turns into cosine, and then it's just v r t. That's d. Now all we have to do is add ct plus dt, and we'll have the answer. So just vt comma r plus this equals, so the path is vt plus r sine vrt plus, or comma, r plus r cosine vrt. And that is the answer. Okay, good. So did we do this right? Let's find out. Hey, it worked. Look at that. And there you go. That's good. This is called a cycloid. And the reason it looks like this is because we have the radius of the wheel and the position on the wheel the same. So if the position of the particle is inside the edge of the wheel, then what's it going to do? See, and now it's just going up and down like that. And then interestingly, if the position is outside of what the wheel is rolling on, let's make it 8, then it actually goes around like that. So, okay. That's cool. So, okay, the other thing that I want to go over today is the velocity vector. If ct is the position function, the path of the particle at time t, then it's reasonable to imagine that the velocity vector of that particle at time t would be the derivative, right? That's how it was in one-dimensional calculus. That's what we've been talking about, is that if this is the position, then the derivative is the velocity. And that is indeed how we define the velocity vector. So the velocity of a path c is defined by c prime of t equals the limit as h approaches 0 of c t plus h minus c of t over h. So we normally draw the velocity vector with its tail at the point ct. So remember, vectors do not have a location in space, but it's just convenient to think of them with its tail at the point whose velocity we are finding. The speed of the particle at this point is just the length of this vector. So the speed is the norm of the velocity vector. So if ct equals x of t comma y of t in R2, then the velocity vector equals the derivative of x comma the derivative of y, or the derivative of x in components, the derivative of x times I plus the derivative of y times j. And the same thing is true in 3 dimensions. If this was in R3, it would be xt, yt, zt, and so on. It's important to recognize that we're not deriving the velocity vector. We're actually defining it in this way. So we're stating that if you take the derivative of each component function, we're calling that the velocity vector. And so the velocity vector, importantly, gives us not only the rate of change, but also the direction of change. Okay, that's also a huge difference from one-dimensional calculus, because in one-dimensional calculus, the rate of change is just the slope. It's just a number. Now we're talking about the velocity vector. So if we accept for right now that limits can be interpreted component-wise, then the derivative of c is just the derivative of the component functions. But it can also be interpreted as the actual limit of the vectors themselves. So when you have c of t plus h minus c of t over h, you can think of the actual vectors. So if you had some graph here, like, I don't know, anything, and we want to know the velocity vector at that point, and down here is 0. So let's say this is ct, and then this is c of t plus h. So we have two vectors here. We have this vector, and we have this vector. So this is also the vector ct, this is the vector c plus t plus h. So if we subtracted this one from this one, that is the vector that goes this way, right? And then as h gets smaller, this vector is going to get closer and closer to this one. That means that this vector is going to get closer and closer until it ends up here at the tangent to this point. So we can actually think of limits actually related to the vectors, that the vector is slowly getting closer and closer to the tangent, just like in one dimension, but with vectors. Or we can look at it component-wise. Next page. So the tangent vector. So basically, all I want to say is that the tangent vector and the velocity vector are the same thing. So the velocity vector c prime is a vector tangent to the path c. So for example, what if we had ct equals cosine t, sine t, and t? Now, without the t, this is a circle. So as t increases, it's going around in a circle, but then we're adding t to it. So over time t, in the z direction, it's going up at the same time. So it's going around in a circle, and at the same time, it's kind of going up in the z direction. It's like a roller coaster. As z is going up, and then it's going around the circle x and y this way and up. So that's called a helix. So let's find what is the velocity vector at t equals pi over 2. Take the derivative of this. We have the velocity vector is minus sine, cosine, and 1. So this is interesting. From derivatives, you can see there's something interesting about this, that it shows you that the change in t is constant, right? We're just slowly going up as we go around. So at time t over, or pi over 2, sine of t at pi over 2 is 1, so it's minus 1. Cosine of pi over 2 is 0 and 1. So at pi over 2, that might be back here, and it's going directly backward in the x direction. It's not moving at all in the y direction, and it's going up. And that's exactly what you'd think, because it's around behind the circle. So it's at this moment moving directly to the left, and it's going upward towards z. So, okay. Okay, one last thing. The tangent line to a path. So if c is a path, its tangent line at t0 is L of t. So the tangent line, so this is an equation of a line, and it's in the same form we just saw a minute ago. This is a point, and then we're adding a vector to it. Remember that c prime is a vector, and this is a point. So we have a point here. So this is ct, and this is C prime t at t0. This is t0, or c at t0. So this is the velocity vector at t0. You just multiply this vector by a scalar with the tail here, and it's going to make a line every value of t going up and down. Okay, the t minus t0, it can look ugly. It just means that we're offsetting, because we could only look at time 0, but instead we're looking at any time, and then this is just offset from t0. Okay, so let's just do a couple of examples. So suppose there's a particle that follows this path, et, e minus t, cosine t, until it flies off on a tangent at t equals 1. So where is it at t3? So what is the velocity vector? It's ct equals, the derivative of et is et. This is minus e minus t, that's the chain rule again, and minus sine t. So we need the velocity vector at t equals 1. So we have 1 equals e, minus 1 over e, and minus sine of 1. Okay, so now we have to make the tangent line, so then we can plug in t3. So the tangent line at t1, so it's a little bit confusing, because the tangent line, now we're looking at time, we're allowing time to vary again, but we're fixing the tangent line at a particular point, t0. So we have c of t0 plus, and then t minus t0, c prime of t0, right? So now we can just plug everything in, because we've done all this. Oh, we didn't do c of t0. So c of t0, let me write that down. So c at 1 is e, comma, 1 over e, comma, cosine 1. So we need to plug this in here. So we have e, 1 over e, cosine 1, plus t minus 1, right? Plug in 1 there, times the velocity vector at 1, e minus 1 over e, and then minus sine of 1. So now all we have to do is plug in 3 here. So this is the line, the equation of the line of the tangent line at t equals 1. So now we want to see where that particle is along that line at t equals 3. So we just plug in 3 here. So L of 3 equals, there's no variable there, so it's e, 1 over e, cosine 1, plus, and then 3 minus 1 is 2, and then again, just the tangent vector. That's the answer. If we wanted to write it in component form, we could have x, y, z. So this is e plus 2e is 3e. This is 1 over e minus 2 over e is minus 1 over e. And cosine of 1 minus 2 sine of 1. That's the answer. Okay, well, there you go. So this has just been a brief introduction to how we deal with curves in space. So we're just looking at how you define a curve mathematically so that you can examine it by using its component functions. So this first topic, vector-valued functions of one variable, was actually pretty straightforward. We were able to define a curve in space and the velocity vector using only what we already know from calculus of one dimension. Now we're going to start looking at the more complicated topics when the function has multiple variables. First, we'll look at real-valued functions of multiple variables, then we'll move on to vector fields. Thank you.
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.